Visual correspondence-based explanations improve AI robustness and human AI team accuracy. Work by Zhang, Mohammad Reza, and Ann from Auburn University. Prototype-based classifiers can be accurate and interpretable class of classifiers, but they used to be tested only on low-res dataset like MNIST or SVHN, or fine-grained image classification of birds or cars, or five-way classification tasks. The second problem is some prototype-based models do not generalize to OOD data as they are highly specialized to learn prototypes. While prototypes can serve as a means for explaining the model's prediction, they do not always improve human decisions accuracy, which is an important objective goal of machine explanations. For example, existing human AI teams often do not perform better than AI alone or humans alone. Do existing prototype-based explanations help humans make better decisions? The short answer is no, because sample images alone fail to help humans tell apart similar classes, here Malamute and Eskimo dog. And they are currently too complex for humans and do not help humans distinguish between AI correct and wrong predictions. In this work, we attempt to address three big problems of existing prototype-based XAI classifiers. That is, we ask how to make prototype-based classifier work on ImageNet and out-of-distribution data, and how to make useful prototype-based explanations for humans and human AI teams. Towards these goals, we introduce a classifier that first explains and then predicts. That is, our model computes how well the input image matches the training set images of each class using patch-level features, and then use them to compute the final prediction. Here, 97% evening grosbeak. For example, the XAI thinks the input bird matches the below evening grosbeak in the yellow eye stripe, dusky neck, and yellow feathers. Our classifier is a semi-parametric re-ranking classifier. That is, first we find 50 nearest images from the entire training set, and then we rank them using patch-wise similarity. Finally, we take the majority vote among top 20 images to make the final classification prediction. Now, let's see how well our simple method works. For thoroughness, we tried two different approaches, namely EMD core and CHM core, for implementing our patch-based re-ranking XAI classifier. On in-distribution data, we slightly underperform ResNet 50 trained on either ImageNet or CUB, but consistently outperform ResNet 50 on out-of-distribution datasets. Across both in-distribution and out-of-distribution datasets, we also outperform a KNN baseline that operates at the image-level features. So, why is our patch-based classifier superior to an image-based KNN? Here is an input image of an ibex that KNN misclassified into parachute, because the input image background matches the cloudy sky in the parachute photos. In contrast, our EMD core model correctly outputs ibex, as it only uses the patches of animal to make decision, discarding the cloudy background. In the adversarial settings, adding an adversarial toaster below the hen results in a wrong toaster prediction. Instead, our classifier ignores the adversarial patch and uses the head and neck of the hen to make predictions. Besides the improved accuracy on OOD test, are our prototype-based explanation useful for human and human AI teams? We performed a large-scale human study in two different settings. In the first setting, we show users the input image, the prediction, and explanations, and ask them to either accept or reject AI's predicted label. Interestingly, on ImageNet, where users are familiar with many object categories, our explanations do not help but hurt human accuracy. Yet, on bird classification, our explanations are useful, helping EMD core and CHM core users obtain the highest accuracy. In the human-AI interaction setting too, where AI labels the high-confidence images, leaving the less certain cases to humans, human AI teams obtain overall accuracy higher than AI alone or humans alone. See our paper for more insights on why our explanations help users. In sum, our XAI classifiers perform slightly worse on in-distribution tests while outperforming ResNet 50 and baselines on out-of-distribution datasets. Visual correspondences are found to be more useful to users than KNN explanations and help users more accurately detect AI's wrong predictions than all other tested methods. For the first time, we showed that it's possible to achieve human AI team accuracy that is higher than both AI alone and human alone on ImageNet and CUB. This research was funded by National Science Foundation, Auburn University, and Adobe Research.